Section 7.2 is about Le Chatelier's principle and upsetting equilibria. And one of the reasons that we're interested in this now is when we start talking about weak acids and weak bases, then we will be talking about things that actually take place with equilibria involved. So we will actually be looking at equilibrium conditions, and it isn't only chemical processes that undergo equilibria, it is also physical processes such as evaporating and condensation. It is also osmosis, it is also diffusion, it is also crystallizing and dissolving a material. These are processes that are involved in equilibria of various types, as well as changing state. And this is a very nice little illustration of that.
A chemical reaction at constant temperature in a closed system is in a state of dynamic equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. Dynamic means the reaction occurs in both directions. Equilibrium means there are constant concentrations of both reactants and products in the system. Consider a wet towel hung out on a line. High-energy water molecules can evaporate and are removed from the breeze. This continues until the towel is dry and can be represented by a simple chemical equation.
For more water to come off.
This is an open system. If the wet towel is left in a closed sports bag, it does not dry. High-energy water molecules evaporate and remain as vapor trapped in the atmosphere around the towel.
But look at the ones that are coming back.
At the same time, low-energy vapor molecules condense on the surface of the towel to a liquid. The rate of evaporation exceeds the rate of condensation until the vapor becomes saturated. At this point, a balance is reached where the rate of evaporation equals the rate of condensation. A state of dynamic equilibrium is reached, represented by a double-headed arrow. Dynamic equilibrium only occurs in closed systems.
Okay, so when we're establishing an equilibrium, we've got the rate of the forward reaction equal to the rate of the reverse reaction. And with that towel situation, until it had reached that equilibrium, it was still evaporating more than it was condensing. And then it reached saturation vapor pressure, where the air would not hold any more water. So then the rate of condensation starts to equal the rate of evaporation, and the towel stays wet. So when you open the bag up, there's your still wet towel that has got some wonderful growth conditions for various molds on it, and you end up with a moldy towel. Whereas if you put it on the line, it would have dried out and it's not got the conditions for the things to grow on it. Now, a system can reach equilibrium whether you start with all of it as reactants or all of it as products. It ends up reaching the same equilibrium so long as it's closed. When it was open, when that system with the towels was open, then the water particles can move away and a fresh lot of air can move up next to it, and then more water vapor can be moved into that air next to the towel, evaporating more. It never reaches an equilibrium. So, but if it's closed, then those particles are trapped inside, and they can't escape. They're there to go back again. Right now, the equilibrium constant shows roughly a ratio between the products and the reactants at any particular temperature. And the only way you can change the equilibrium constant is to actually change the temperature. Catalysts just get to it faster. They don't change its position. Pressure doesn't change it, volume doesn't change it, adding one thing does not change it. Remember, there are multiple ways of getting the same number in your equilibrium constant. Now, with this particular one, if you start out with a petri dish containing potassium iodide and you add some just ordinary iodine into it, you will actually dissolve some of the iodine, the I2, into it, and it'll become a brownish colour. And once you've reached, this is very similar to the towel, once you've reached the position where the amount of dissolving equals the amount of recrystallizing, then that solution is saturated. Now, supposing you take out those pieces of solids and you put in some new pieces of solid that don't have any radioactivity in them. So this is now a radioactive solution because the first lot was radioactive. This is now a radioactive solution, and we're putting in here some unradioactive iodine in here. So what's happening here is that you're still getting the dynamic equilibrium. You're still getting something to dissolve at the same rate as it is reforming the crystal. So that when you take this fresh, nice piece of iodine out of here, pat it dry, and check it with a Geiger counter, you find that you're actually getting radioactivity inside the crystal where there was none to begin with. So that can only possibly be happening if there is constant dissolving and recrystallizing between the solution and the crystal, just in the same way as the water particles in the air over the bag were continuing to dissolve, to condense and evaporate. Now, this system looks very like the model that we made up, and this is a real chemical system where we're using nitrosyl bromide, which is colourless, and it makes nitrogen oxide, which is colourless, and bromine gas, which is orange. So we can track the progress of this reaction by tracking the intensity of the orange that is produced, and that's how they get these readings on here, and they get the equilibrium position. Again, it doesn't matter if we start out with it as all bromide or all nitrosyl bromide, we will end up with the same equilibrium position. So having established the idea of equilibrium, we know what's going on. Le Chatelier says, well, what happens if we disturb a system at equilibrium? We do something that makes a change to the system which was at equilibrium. We've shifted it out of the most energy favorable situation. It wants to get back to, well, it will get back to that energy favorable situation by reversing or countering what we have done. Well, it won't reverse it completely, but it comes fairly close. Now, there are a number of ways we can disturb a system at equilibrium. We can change its temperature. We can change the concentration of one or more of the reactants or products. We can change the overall pressure or the volume of a gas. A catalyst really doesn't alter the equilibrium. It just gets there very much faster. Today we saw that you can have copper sulfate and it's hydrated. And the hydrated copper sulfate in here is a blue color. If we added the hydrochloric acid, it's concentrated hydrochloric acid, so there's a lot of chloride minus ions that crowd around this copper 2 plus, and they push away the water particles, and they form the green-coloured complex ion, and that's what we saw today. When we added more water, the system used up some of that water to remake the the copper chloride and the copper hydrated, and that made it blue. So we spent a bit of time pushing it backwards and forwards. The other one we spent a bit of time on was the dichromate ions. And there's the dichromate. It's got two of these chromates together, joined through an oxygen bond, and it's kind of lost a water molecule to do that. Now, the dichromate is the yellow one, and the chromate is the orange one. Okay? So if I added acid to this, then the system, which was once at equilibrium, will now use up the excess acid, take the yellow chromate as it uses it, and make the solution orange, because it's trying to get rid of the extra H+. But as it does, as it uses this at the same time, and it makes the orange dichromate. Similarly, if I put in there OH minus, hydroxides are going to use this up. This is going to be reduced. We're going to be taking this away. If we're taking this away, the system remakes H pluses, and it remakes H pluses by shifting to the left. And what happens there is then the chromate, which was orange, so dichromate, which was orange, becomes chromate, which is yellow, at the same time as it makes the H plus that it's replacing. So the solution goes from orange to yellow. Now, the final one we're going to look at today is the dinitrogen tetroxide, which is another dimer. If you have energy with it, it produces nitrogen dioxide, which is this kind of a brown gas. The dinitrogen tetroxide, some people say it's yellow and other people say it's colorless. And that basically you can't get it to be completely on its own because it will instantly make a little bit of this, which is yellowish, yellow-brown. Now, we looked at it and we saw it in the ice, that actually when we put it in the ice, it kind of lost the colour. And it's losing the colour because when you put it in the ice, we're drawing energy out of that container, out of those particles. So the system's trying to remake energy going back that way. As it remakes energy, this brown gas is turning into this colourless gas at the same time, making the whole thing a much paler colour. When I put it in hot water, which is going to happen tomorrow, the more hot water I put in there, I've suddenly increased the amount of energy. The system is going to try and use up that energy going back that way. Now, when it's using up the energy, at the same time as the energy is going, so is the dinitrogen tetroxide, and it's becoming nitrogen dioxide, which is that brown gas, and it becomes much more intensely brown, as you can see there. Well, that's enough of Le Chatelier's principle for today. It's a big idea, and we'll do a second tape on that.